Welcome. This is the third lecture from the Risch diagram, and there is the heat and material balance for blast furnace iron making. And this lecture will cover the Risch diagram based on heat and material balance in the Wüstide reserve zone, right? And the basic concept covered basically blast furnace as a two-stage reactor. This is very important. We have to understand that blast furnace can be conceived as a two-stage reactor, and then we will develop a fully predictive model for the blast furnace. That is the operating line, a fixed operating line with two fixed points on the operating line such that it is fixed. So, coke rate, minimum coke rate we can calculate from there. This is basically we will discuss. Now, conceptual definition of the blast furnace through isothermal and chemical reserve zone. Now, if you see, that is the first diagram. If you see the diagram 1, this is one, this is the diagram. If you consider, then this is basically the temperature profile of the solid. This is solid line is for the solid, and the dotted line represent the gas temperature profile as it moves up, as the distance as you move up above the TUER line. This is basically the TUER, this is basically the TUER, this is the TUER, and as you are moving up in the TUER, sorry, this write up is not very good, so I will write it TUYER, I think now it is. This is the TUER location, and is as we moving up distance above the TUER, right. This is the distance above TUER line. So, what you can find is that here you can find that the gas is entering at around it is the temperature in Kelvin. This is around 2200 Kelvin. 2200 Kelvin is around say 2000 degrees centigrade. Basically, the gas in the combustion zone, the gas temperature, blast furnace gas temperature is around 2000 degrees centigrade or 2273 like this, or 2300 Kelvin, right. So, here the gas temperature. Now, the gas from 2000 degrees centigrade to it is around 900 degrees centigrade, 1200, you can see 1200 is basically around 900 something. So, 900 degrees centigrade. So, gas temperature you can see decreases from 2000 degrees centigrade to 900 degrees centigrade, where the solid temperature increases from 900 to 1300 degrees centigrade in this lower part of the furnace. So, obviously, in the lower part of the furnace, why it is like this? Because the heat capacity of the solid is very high, because a lot of endothermic reaction goes on. As a result, the heat demand of the solid is very large. So, the solid temperature increase from 900 to 1300, while the gas temperature decreases from 2000 to 900 degrees centigrade within a very short distance in the lower part of the furnace. Within this much distance, all these heat exchange take place in the lower part. After that, you can find in this zone absolutely the temperature difference between the gas and solid is not that much. Okay. So, as a result, no significant heat exchange take place, and this region the temperature is almost constant. In this region the temperature is almost constant, and it is called the thermal reserve zone or isothermal zone. You can call it also a isothermal zone. So, it is called the isothermal zone or the thermal reserve zone, a significant portion of the blast furnace where temperature of the solid and gas almost remain constant. And theoretically speaking, that is the practically speaking, it can be 800 to 1000 degrees centigrade, but average temperature you can say 900 degrees centigrade. So, in this region the temperature remain constant at around 900 degrees centigrade. This is called the isothermal zone or thermal reserve zone. And in the upper part you can find again the solid temperature increases from 30 degree to 900, where the gas temperature decreases from 900 to around 200 degree or 150 degree centigrade. Okay. So, there basically obviously the heat capacity of the gas is more than that of the solid, and the heat capacity of this gas is more than that of the solid, because the decrease in gas temperature is less compared to increase in solid temperature in the upper part. Anyway, but here also some heat exchange take place in the upper part in this region, and in the lower part heat exchange takes place in this region, and in the middle zone, this much of zone, absolutely no heat exchange take place almost, and the solid and the gas temperature remain almost at 900 degrees centigrade, right. Now, so you can simply think that is the blast furnace can be divided into two parts, and we can make a separate heat balance for the upper part as well as lower part. In this zone, basically no heat exchange take place. That is one thing. Now, it is from heat transfer point of view. If you see the chemical composition of the gas composition, how does it vary longitudinally as you move from the tuer above this, above the tuer. So, how does it vary? You can find the gas O by C ratio is equal to 1, means the product gas is basically CO. When the gas is completely CO, 100% CO, then O by C ratio is equal to 1. So, O by C ratio, you can see it is almost 1 up to this portion, that is only CO, basically CO2 is not there. Whatever the CO2 produce because of reduction, it immediately get converted to CO by carbon gasification, right. CO2 gasify the carbon to CO gas. So, obviously reduction is taking place, but immediately the CO2 generated from the indirect reduction, that is used up to gasify the carbon to CO. So, the gas composition almost remains CO up to this point, and beyond this point you can find that the CO2 is coming into the system. CO2 is coming in because the carbon gasification reaction slows down as you move up. As the temperature decreases, then this reaction, that is the CO2 in situ generation, this reaction is called the carbon gasification reaction. It intensity, basically its intensity goes down as you move up. As a result, the CO generation decreases, but CO2 is continuously forming because of ore reduction. There is indirect reduction of the ore, your CO2 is generating, but this generation of CO is not that high. As a result, the gas is accumulating CO2. So, as the gas CO2 is increasing, your O by C ratio increasing. O by C ratio is increasing, indicating that is the CO2 in the CO2 gas mixture is increasing, right. So, with increasing and then you can find again the O by C has become constant during this region. In this portion, O by ratio and O by C is around 1.3. O by C ratio is 1.3 and it is constant. What does it mean? Basically, in this case here what happens that this reaction become in equilibrium, that is the FeO plus CO basically forming Fe plus CO2. So, up to this portion there is a direct reduction. Beyond that, indirect reduction is taking place. Basically, whatever the CO form in the lower part, that is used up into the indirect reduction, and you are generating the CO2, and this CO2 basically accumulating into the gas, your O by C ratio is decreasing, and then it become constant for a certain length of the blast furnace. That is called, and then that portion, this come into equilibrium. This reaction come into equilibrium, and I know this reaction when it comes into equilibrium, this reaction, equilibrium reaction, if you write as I said in the thermodynamic class, that is the blast furnace, then what I say what we found is that basically for this reaction, for this indirect reduction, CO utilization is only 30%. CO utilization is 30%. Basically, this reaction we write in this way: FeO plus 3.3 CO is forming Fe plus 2.3 of CO plus CO2. Basically, out of 3.3, basically if you want to remove 1 gram atom of oxygen, you require 3.3 mole of CO, only out of which 2.3 mole of CO will remain in equilibrium with the CO2, and only 1 mole of CO will be used up to take out the ore oxygen. Okay. So, that is the thing we have seen, and so basically if we write it in this fashion, what is your O by C ratio? What is the O by C ratio that you can find? Basically, we know that is only 30% CO is utilized. Basically, CO2 by CO plus CO2 is only 0.3 for this reaction, and this corresponds to basically 2.3, and CO by CO2 ratio is 2.3, CO by CO2, this ratio is equal to 2.3, CO by CO2 ratio is 2.3. And from this corresponds to O by C. If you calculate the O by C, that will be 1. You can simply calculate it and you can see O by C will be 1.3. So, this O by C is equal to 1.3 basically represent a equilibrium, that is this equilibrium is represented by this O by C is equal to 1.3. So, what I want to mean is that you are at this point. So, this region, that is the FeO plus CO, this reaction come into the FeO, Fe, this reaction become in equilibrium, they come into the equilibrium condition, equilibrium. So, you can find this is also called the chemical reserve zone or the chemical inactive zone, you can say. So, in this region you can see, so if I cut this blast furnace this way, in this reaction there is a separate heat balance, there is a, you can simply do the separate mass balance also, because I have an equilibrium line here, that is here I have an equilibrium. So, this portion come to an equilibrium also. So, I can separately make a heat and material balance on, this is also called the Woods-Tide reserve zone. This portion is called the Woods-Tide reserve zone, because Woods-Tide FeO, Fe comes into equilibrium in this zone. Okay? And also I can do a separate heat balance. I do not require this up part, because I can perfectly do a separate heat balance here, and also you can see this O by C ratio also become constant in the upper part of this zone. Okay. So, I can make a separate heat and material balance on this Woods-Tide reserve zone, and from there I can derive the operating line. So, that I will be doing basically. So, now you can see this is the scenario, this is what, this is the blast furnace. If you can this is the way you can divide the blast furnace in two parts, this is the upper part and the lower part. Okay. And this is called the Woods-Tide reduction zone or Woods-Tide reserve zone. Okay. So, here what are the input you can find from there in the upper part, here when the input is Woods-Tide, basically solid will come as Woods-Tide. Here you are entering in the upper part, you are entering the Fe2O3, entering Fe2O3. Now, Fe2O3 will convert to Woods-Tide in this region completely, and then the Woods-Tide, because Fe2O3 to Fe3O4, Fe3O4 to FeO, and this FeO will enter in the Woods-Tide reserve zone at 1200 Kelvin. 1200 Kelvin means around 900 degrees centigrade. Okay. So, Woods-Tide will enter into this, and then the carbon will also enter at 900 degrees centigrade or 1200 K, and the gas will also exit at 1200 K, and the gas composition is also fixed, O by C is equal to 1.3, because upper part of the Woods-Tide reserve zone FeO Fe equilibrium is established, where O by C is 1.3, right. So, this is also known to me now, and your air blast is coming through here at 1400 Kelvin, okay, and the liquid iron is leaving at 1800 Kelvin. So, this is the system. So, I will just make a heat balance of the Woods-Tide reserve zone, heat and material balance, and I can get the operating line. Okay. So, based on this data, again I can do later on the heat balance in the upper part, heat and material balance. So, that will give me actually what is the exit gas temperature, what is the exit gas, that is those things, temperature also you can get. But exit gas composition from here also you can just extrapolate the line and you can get the exit gas composition also. So, now let us go to this thing, that is the first, let us do the enthalpy balance. Now, this is for the material balance. If you see the material balance, okay, if you see the material balance is okay, this is NOB, that is NOB means that is the blast oxygen that is coming in per gram atom of iron produced. And what is the oxygen coming through the iron ore? Ore is Woods-Tide, and 1 gram atom of Woods-Tide contain 1.06 gram atom of oxygen. So, this plus this, okay, this is from the blast oxygen, this is the ore oxygen is equal to NCA active rate of carbon into O by C, this is O by C, and O by C is equal to 1.3. So, this is the simple material balance in the Woods-Tide reserve zone, right. Now, let us do the heat balance, and heat balance I have seen, just if I know what is the demand and what is the supply, I can equate, that is the enthalpy balance will be done, right. I will do better that way. So, what is the total enthalpy balance, that is the what is the demand in this case, let us see. So, demand is this thing, these are the Wüstheit zone, reserve zone demand. First is the decomposition of the Wüstheit, because Wüstheit will come and that is decompose, and for gram atom of iron you require basically 1.06 mole of Wüstheit, right. So, multiplied by the heat of formation of Wüstheit, that is just reverse of decomposition, that is why a negative sign has come here. So, this thing is basically a positive number finally. So, this is the heat demand for Wüstheit decomposition. And then what is this? This is basically sensible enthalpy of liquid iron, that is the liquid iron, standard enthalpy of liquid iron at 1800 Kelvin minus that is the standard enthalpy of the solid iron at 1200, because iron is entering at 1200 degree centigrade with the Wüstheit. Along with Wüstheit, you are entering basically the iron is entering in the form of Wüstheit at 1200. So, that is why this is there, and this is, and finally, the iron is leaving in the form of liquid form at 1800 Kelvin. So, standard enthalpy of liquid iron at 1800 minus the standard enthalpy of solid iron at 1200, that is entering, right. And plus what is that? This is the two heat demand, one is decomposition and the sensible enthalpy, sensible and latent enthalpy of iron that you are giving, plus some amount of carbon. Carbon is entering at 1200, a part of the carbon going to the hot metal. So, that we have considered here, and how much carbon is going, C by Fe, that gives you, that is the percentage of carbon that is going into the hot metal, C by Fe, that is the carbon per gram atom of iron that is into, that is the enthalpy, standard enthalpy of dissolved carbon, that is in this thing at 1800 minus standard enthalpy of solid carbon at 1200, that is entering, right. So, this is basically the demand term, and plus you have other term, another two term will be there, plus delta H of the slag because of slag formation, plus delta H of the loss, and because of loss through the furnace, lot of losses are there. So, another two term will be there. This is the total heat demand. Now, if you consider the supply term, then what are the terms that we have? So, supply, what are the supply term is there? Then in case of the supply, you see what are there. One is that heat of formation of the CO, and the CO gas is leaving at 1200. So, heat of formation of CO at 1200 and heat of formation of CO2 at 1200, and with their multiplied by their respective moles of CO and CO2, that is one thing, that is basically the heat generation, that is the supply. Another supply term is there because of sensible enthalpy through the air blast, because air blast is entering at a higher temperature 1400 Kelvin and it is leaving at, and the nitrogen basically, nitrogen and oxygen entering at 1400 Kelvin and then leaving at 1200 Kelvin. So, you have some sensible enthalpy. So, that is also will be there. So, that can be calculated in this form, that is the NOV. NOV is basically the kg atom of or gram atom of oxygen that is entering, okay. And half is there because half term is coming because of this. This is basically the oxygen, standard enthalpy of oxygen is 1400 minus standard enthalpy of oxygen at 1200. So, this is, and half you are doing because NOV is gram atom, okay. So, 2 gram atom of oxygen make 1 mole of oxygen. So, that is why half term is coming, and plus the nitrogen also, nitrogen entering, there is a standard enthalpy entering at 1400 minus nitrogen leaving at standard enthalpy of nitrogen at 1200. So, this is the sensible enthalpy of nitrogen that is giving into the Wüstheit reserve zone, sensible enthalpy of oxygen that is also given to the Wüstheit reserve zone. So, this is basically the sensible enthalpy that is coming through the blast, and this is the enthalpy generation because of carbon oxidation to CO and CO2. This is the total supply, and this supply, if you write in this form in the algebraic manipulation, you can write in this form finally, okay. So, EB stands for this term, basically your EB is this term, this is the EB, this is the EB term, this is called your EB, that is the excess enthalpy of the blast, that is called the EB, excess enthalpy of the blast, that is defined like this, and including the half of this thing. So, NOV into EV is coming from there, and this term if you rearrange in terms of O by C, you can write like this. That is the simple algebraic manipulation. And so, finally, you can write this is equal to, you can write like this, that the NCA into this plus NOV of this. Because if I put the value of enthalpy of formation of CO, enthalpy of formation of CO2, sorry, okay, this is the supply. And then let us see the combined form of Woods-Stite reduction zone. If I use the combined form, that is the material balance and heat balance, if we just combine and we eliminate the O by C from both of them, and then finally the heat demand in the Woods-Stite reserve zone can be correlated like this, and some algebraic manipulation you can come here and finally here. Okay. So, these are just algebraic manipulation. What I have done, demand is equal to supply, and also I have eliminated the O by C from the material balance and the enthalpy balance, right. So, finally, you can get that, and you can get this equation, and this equation you can find here also, you can write like this, that is y 2 minus of this is y 1, okay, is equal to m of x 2 minus of x 1. So, you can write in this form the equation where y 2 is equal to 1.06 and y 1 is whole term is basically this is whole term, this whole term is this is y 1. So, wait whole term, this whole term is equal to y 1 and this term is y 2 and is equal to m into x 2 minus x 1, x 2 is basically this and x 1 is this whole term, right. So, again it is a straight line, but you can find that is the x 2 x 1 and y 2 y 1 all are defined, all can be defined. There is the two fixed point on the operating line. So, we have two lines you can find from there, as I say y 2 minus y 1, x 2 minus x 1, and then 2 points we are getting, that is the x 1 y 1, this is basically x 2 and y 2. So, A and B 2 points are there on the Riesz diagram. So, you can find 2 points I have got, one point is that, one point is this one, this is basically there is the point B, this is the point B, this is the point B and this is the point A. This is 1.3, 1.06, this is the point A and this is the point B. So, also this point here A and B I have written, basically here we are calling it as H. H is the thermal pinch point and W is another point, I am calling it A also here. Basically that is basically W is basically called the chemical pinch point. This is another point is there. Basically this source, that is this thing is basically the FeO equilibrium, FeO equilibrium line, that is at 1.3 basically FeO and the gas composition 1.3 means that is then the equilibrium point for FeO reduction. This is the equilibrium point. So, if the line can never go like this. So, if I want to draw a line like this, so this is not a feasible line. This is not a feasible line from this point of view, because this line will not satisfy this equilibrium point of FeO equilibrium. Okay. But any line like this, if I can draw like a line like this is feasible, this is a possible line. But this is the optimum line, this is the optimum or minimum coke rate, optimum or minimum coke rate. This gives the optimum minimum coke rate, but this line is feasible. All these three lines are passing through this H, passing through this line is possible, but this line is not possible because it will not, okay, this line will not satisfy this point FeO equilibrium. This line will not satisfy, this line will satisfy, and this is the optimum line. So, now we get that this is the thing, that is by doing the Woods-Stite reserve zone heat and material balance, I get basically 2 points. One is called that is called the thermal pinch point H, another is called the this point is called the chemical pinch point. This is the thermal pinch point, and this is called the chemical pinch point. And the line has to follow both this line. Okay, the line has to follow, but you can have a other line like this line is possible, as I said, but this type of line are not feasible. No line can go beyond this point. That is the thing. No line can go beyond this point, this direction. Line can move, but that will be less efficient line. But this is the most efficient line. This optimum line is the most efficient line. You can have some less efficient line, as I said. This is the feasible but less efficient. Feasible but less efficient. This is the feasible and most efficient. And a line, what I is telling is that a line like this is not possible. A line like this is not possible. So that is the thing what I want to say. I have just repeated twice. And so now some problem, that is a problem is a blast furnace is operating with the dry hot air blast at 1400 Kelvin. The charge consists of hematite, sinter, CO, coke. Its product metal contain 5% carbon, and its slag may be considered consist of CO and SiO2. All these things are given basically. So you have to calculate from there. This problem is we have solved it. And so Woostead reserve zone. So what is basically the, you have to first calculate the demand. All the terms are given here. So you calculate the demand, and to calculate the demand, basically you can see here all the demand term I have added. One is the Woostead basically decomposition, then the sensible and latent enthalpy of iron, then the sensible latent enthalpy of the carbon, and then the heat loss due to slag and heat loss due to the atmosphere. Okay. And according to this problem, I can calculate the weight of the silica and the weight of the calcium oxide, and then total weight of the slag. And based on the total weight of the slag, we can calculate what is the enthalpy of the slag, that given minus 400 per kg of slag. So you can get that thing. And the heat loss also, one formula is there. From there we can calculate it, because basically this is this much of kg joule per kg mole of iron produced. This will be the heat loss. From that formula you can simply calculate. So finally you can calculate what is the total heat demand of the direct reduction Woostead reserve zone by this formula. So this will be around 347,000 kilojoule per kg mole, and excess enthalpy of the blast also you can given, you can calculate. These value are taken from the literature. So you can do, that is around 17,000 kilojoule per kg atom of oxygen. Okay, per kg atom of oxygen will be the excess enthalpy. Okay, and multiplied by the NOB, that will give you the excess enthalpy that is coming out, 17,000 kilojoule per kg mole of iron produced, multiplied by the NOB then. Okay. So then Woostead reserve zone, you have this point, there is a thermal pinch point, you have the this is the chemical pinch point is known, is constant 1.3, 1.06, because basically this is the Woostead equilibrium composition. And then the thermal pinch point is given like this. You need to know what is the heat demand and the EB, and both the term we have calculated already. So we know those values, put those values, so you can get the thermal pinch point also. Then in CA you can simply calculate here, because 2 points, 2 fixed points. So slope is constant, that is the slope 1.648. From there you can calculate the coke rate, that is the kg per ton of, this is basically kg atom of iron per kg atom of kg atom of carbon per kg atom of iron produced. Just convert it to kg of carbon per ton of iron, right. So then you can get the coke rate. Then you can get the blast rate also. NOB you can calculate, slope you know. So NOB you can calculate, from NOB you can calculate the blast rate, there is a normal meter cube. And then you can have O by C also you can calculate, because slope you know. So simply you can get the O by C, and then you calculate number of moles of CO, number of moles of CO2, number of moles of nitrogen, and then simply the gas composition you can get. So this is a simple example, and these notes are there, you can follow it. So what we get from there, so this is also from the Davenport. If you have, this is the ebook is available, ebook is available free of cost in the internet. You can download this book and have this. So conclusion is that heat and material balance system Woostead reserve zone makes the operating line of risk diagram fixed with 0 degrees of freedom and a fully predictive model. Fully predictive model means in the line we have 2 point, and 2 point makes a straight line fixed. So we have, so we can have a what is that called, the minimum or optimum coke rate, but the furnace can operate along the fulcrum of the thermal pinch point, but it can be less efficient only. If the line moves on the left hand side, it is less efficient. On the right hand side, line cannot move, because then you will not satisfy the equilibrium requirement of the FEO-FE system. So this is all. Thank you very much, and you consult the book of Davenport, and that will be helpful. Or Professor Deepak Majumdar, one book is there that is also nicely described all this what is that called, heat and material balance. And some intricacies are also there. For example, the silicon reduction and the phosphorus reduction we have not considered, those oxygen we have not considered, but we can easily incorporate into those. And this model can be extended for suppose pulverized coal injection, and then we can change the material balance, and then we can. So for any condition, this risk diagram can be little modified for your blast furnace situation, and then you can predict the optimum coke rate, you can predict what is the gas composition, and what is the blast rate, and all these things. Hopefully, this lecture will be helpful for heat and material volume balance and calculating different important parameters in the industry. Thank you very much.